Our problem this time involves an ellipse there, x squared on 4 plus y squared equals 1. And we've got the cross sections being an equilateral triangle. So all three sides are all equal. So again, if we get one side, we can try and find our perpendicular height, or we can use trigonometry to get our cross-sectional area. The cross-section is perpendicular to the major axis, so that's why it was saying, well, the major axis is along the x-axis, it's perpendicular here, so that's why we're going to have delta x. Again, we've gone across the distance of x, so we go y in that direction, y in that direction. So minus y to y gives us 2y along our side. So the sides of our triangle are 2y all the way through. And a few ways we can use Pythagoras' theorem to get root 3y, and then half the base times the perpendicular height. Or we know that this angle there would be 60. And so we're looking at 2y and 2y as our sides. Half times the product of those times sine of 60 gives us root 3 y squared. So there's our area there, root 3 y squared. So you can do it by the area formula with half the base times the perpendicular height, or do it with the area with trigonometry. Y squared is equal to the 1 minus x squared on 4. So then we put it back because we're in terms of delta x. And we're going to sum between minus 2 and 2, or two lots of 0 to 2. So we have our root 3 out the front from what we had before, and the 1 minus x squared on 4, integrate there, sub in 0 and 2, and we get our value. Our ellipse here this time has not an equilateral triangle, but it has an isosceles right angle triangle. Again, we're starting to get the idea that we're going to have our base being 2y. It's delta x because it's perpendicular to the major axis. And so from our isosceles right angle triangle, again, use trigonometry to get your sides and your area, or you could use some other methods that you'd like, Pythagoras' theorem. So we get the area of this as a half times the root 2y times root 2y. So in cleaning that up, that just gives us the y squared. So the half times the 2 is going to cancel. We just get the y squared, which is 1 minus x squared on 4 times the delta x. We integrate again between minus 2 and 2, so we're going to take two lots of 0 to 2. The 1 minus x squared on 4, which will come down to 8 on 3. Question 7 here. We've got a parabola, which is our base, and we have area that's bound by its vertex and its latus rectum. So the latus rectum, we know a is equal to 1, so that's why we get the x equal to 1 there. Every cross section is perpendicular to the x-axis is a square this time. So we've got our square, 2y, 2y there. Because again, we've gone across x and to y. And we've got our function and relationship between x and y squared and x to the power x. Y squared equals 4x. So we've got that situation. We've got our cross-sectional areas 2y times 2y, which gives us 4 lots of 4x, which gives us 16x. And so that gives us a volume formula of 16x delta x. And we're going from 0 to 1 because we had the line x is equal to 1, so 0 to 1 of 16x gives us our function there. This time we've got our base being x squared plus y squared equals a squared. So a little bit different. We've got no numbers to play with. But we've got each cross section being a square with one side on the base of the solid. So again, we're getting our 2y times 2y. We should be getting that idea now. But we're going from minus a to a from our integration for our x values. So we get 4y squared, and y squared is a squared minus x squared from our function here. And so we put it in terms of x because it's delta x, and then we're integrating from minus a to a, which becomes 2 lots of 0 to a. And the 4 there, so we can round 4 out the front and multiply to give us 8. And then integrate with respect to x. We're not integrating with respect to a. A is a constant, x is the variable, so we integrate with respect to x. Between 0 and a, we sub it in, and we're going to get 16a cubed on 3 units cubed. So again, the process stays the same even though there's no numbers. So we get our cross-sectional area, we're making sure we've got our thickness correct, so we know which variable we're going to integrate with respect to, and we've got to put our function in terms of. We make sure we get our terms of our integration correctly after finding the correct area, which allows us to get the volume.